Dear students, welcome back. We have reached the second part of section 5.2.1, and there we introduce Girsanov's theorem. Girsanov's theorem in one dimension. Well, Girsanov's theorem is important in financial mathematics because it allows measure changes of measure for financial price processes, and we will be seeing that we will use them a lot. There is also a multidimensional Girsanov theorem, and we will see that in a later video lecture. But first, let's do a short motivation for Girsanov's theorem, because in fact, we have seen it already by the end of chapter 1, where we have shown the following. We have shown that if X is standard normally distributed, so with mean 0 and variance 1, on the probability space omega fp, and if we define another random variable y being equal to x plus theta, then of course we have shown that y is also normally distributed, but now with mean theta and variance 1 under the measure p. However, we have shown for a function z, for a random variable z, however, we have shown that for a random variable z being defined as e to the power minus theta x minus 1/2 theta square, that the probability of z greater than 0 is equal to 1 almost surely, and moreover that the expected value of z is equal to 1. And then we are in the setting of the previous video lecture with the probability of z greater than 0 equal 1 and the expected value of z equal 1, we can define a new measure. So we have defined p tilde of a as the integral over a of z dp, with z the function over here, the exponential function defined over here. Of course, this integral is equal to the expected value of the indicator function of a times z, and that is identical, of course, to the integral over a of e to the power minus theta x minus 1/2 theta squared dp. Then we have derived at the end of chapter 1 that under p tilde, y is in fact standard normally distributed, so with mean 0 and variance 1. That was a particular example, and now we want to do it for a whole process. And that is Girsanov's theorem in one dimension. So let's first have the setting. We have a Brownian motion, Wt. Little t runs from 0 to capital T, say the end of a financial contract, capital T. Let that be a Brownian motion on our probability space, omega fp, with a filtration script ft and t again from 0 to capital T. Now let theta t, little t between 0 and capital T, be an adapted process. And here we define our random variable z as follows. Zt is the exponential function with as exponent minus the integral from 0 to t, theta u dwu, minus 1/2 the integral from 0 to t, theta square u du. And here we assume that theta t is sufficiently nice, and later in a few lines from now we will explain what that means, but essentially it means that this Ito integral exists and also that the Lebesgue integral exists. Let's define another process, w tilde t, and that is wt plus the integral from 0 to t, theta u du. So this is our setting. We have w, we have theta, we have zt, and we have w tilde. And we need to assume for the integrals to exist that the expected value of the integral from 0 to capital T, theta square u, z square u, is finite, exists. because that guarantees that the Ito integral is well defined. We will not go into detail, we just need some condition. Moreover, in our notation, we will use Z for ZT. So Z at final time t. Then Girsanov's theorem in one dimension tells us that, first of all, the expected value of Z is equal to 1, and that the probability of Z greater than 0 is equal to 1 almost surely. Moreover, it tells us that the process W tilde, where little t runs from 0 to capital T, is a Brownian motion under P tilde, where dP tilde is equal to ZdP, and in our notation that is equal to ZT dP. So how do we prove that? Well, we first will prove 1. So the expected value of Z equal 1 and the probability of Z greater 0 under measure P equal to 1. Well, first of all, it's clear that Z is non-negative. If we look back at Z, we see that it's an exponential, so it's certainly non-negative. Now we need to prove that the expected value of Z is equal to 1. And we will do that by showing that the process ZT, with small t between 0 and capital T, is in fact a martingale under P. Yeah, if we are able to show that this is a martingale under P, we know something about the expectation, right? We know that the expectation of Z, that is then by definition the expected value of ZT. And when it is a martingale, we know that this is equal to the expected value of Z0. And because we are dealing with an exponential here, then if we substitute 0 in left and right hand side, we end up with 1. So then we have that the expected value of Z is equal to 1, and that is exactly what we want to achieve here. And we will do that by showing that CT is an Ito integral. And we did that before, so we know how that works. So to this end, showing that it's an Ito integral, let's consider the exponent. The exponent is, and we call it x here for a change, we call it x, and that was the exponent of Z minus the integral from 0 to t theta u dwu minus 1/2 the integral from 0 to t theta square u du. And in differential notation, we know this, this is dxt is equal to minus theta t dwt minus 1/2 theta square t dt. Here you see it, dxt equal to minus theta t dwt minus 1/2 theta square t dt. Now we want to show that e to the z is an Ito integral, and with this we can use the Ito-Dublin formula and show that by Ito-Dublin formula that we're dealing with an Ito process, in fact. And for this it makes sense, it's most natural to choose our f as e to the x, and for x we then substitute this exponent over here. And with fx e to the x, we know that the first derivative with respect to x is equal to the second derivative with respect to x is equal to e to the x. And these are just nice derivatives that are continuous and they exist. So by the Ito-Dublin formula, we can look at e to the x. So z is e to the x, and we look at dz, dz, and that is the change in f, so df xt. And here we first write down how it was again. To remind you, it is df dx dxt plus 1/2 the second derivative of f with respect to x, dxt dxt. And for little x, we have substituted xt. Now we can substitute the things that we know. Fx here is in fact our function e to the x, so that is z itself. So this is equal to z dxt plus 1/2, and here also we substitute z times z times dxt dxt. Well, for dxt, we know its function. It's written down here, so we can substitute that. And for dxt dxt, think of dxt dxt. We have a dwt term, and that is the only one which is non-zero. The mixed term is 0. The dt squared term is equal to 0. So you will see that dxt is in fact theta squared t dt. So let's substitute these two expressions that we know. So here this is equal to zt times dxt times minus theta t dwt minus 1/2 theta squared t dt plus 1/2 zt times dxt dxt, and for that we can substitute theta squared t dt. So what do we have now? We have this term here, zt minus 1/2 theta squared dt, and we also see that appear here. So they cancel out, and in fact what remains is minus zt theta t dwt, and that is what we want to see, right? That is an Ito process, and so equivalently, right, the integral formulation is like this. Zt is equal to z0 minus the integral from 0 to t zu theta u dwu, and this is an Ito integral. It's clear this is an Ito integral. Zt, little t between 0 and capital T, is an Ito integral under P, and hence it's a martingale under P. So then we have immediately our first statement. The expected value of z is by definition the expected value of ct, and by the martingale property, that is the expectation of z0, and we have seen and we have explained to you that this is equal to 1. So that statement is also proved. Now the second proof, so let's look at the second statement again to remind you. The second statement was that the process W tilde t, little t between 0 and capital T, is in fact a Brownian motion under P tilde. So how do we prove that? The second statement. Here is the second statement. How do we prove that? Well, we want to prove that W tilde t, little t between 0 and capital T, is a Brownian motion under P tilde. And for that, we will use the Levy characterization from the previous lecture. So we want to show that it is a so in order for this to be a Brownian motion, it needs to be a martingale, it needs to have continuous paths, and it starts at 0. So first of all, clearly W tilde 0 is equal to 0. That's the first condition in the Levy characterization of Brownian motion. Yeah. Secondly, W tilde t has continuous paths. Yeah. So it is. Let's look at the definition again. Here is the definition. W tilde t is equal to Wt plus the integral from 0 to t theta u du. It has continuous paths. And thirdly, we have to say something about the quadratic variation of W tilde. That should be equal to t. And here we say that the quadratic variation of W tilde is equal to the quadratic variation of W, and that is t. So in fact, if we write it out, but from the definition of W tilde, we see that dW tilde t is equal to dWt, and that is equal to dt. So that is also guaranteed or satisfied. So our three characterizations are satisfied. So the only thing left to show is in fact that W tilde t, little t from 0 to capital T, is a martingale under P tilde. And also we do that in two parts. We first start by showing that this W tilde T is a martingale under P. And then we will be using lemma 5.2.2 from the previous lecture in order to prove that W tilde T is a martingale under P tilde. So we first want to prove the first claim that W tilde T times CT is a martingale under P. And the proof of claim 1, we do that by Ito's product rule. We have the following, we have that d W tilde T CT is, by Ito's product rule, it is W tilde T dCT plus CT dW tilde T plus the correlation dCT dW tilde T. Now substituting everything we know, so recall that dZ is equal to minus C theta T dWt, and moreover dW tilde T is equal to dWt plus theta T dt. Now using the Ito product rule tells us that dW tilde T ZT is W tilde T dCT, so here we find this one back, plus ZT dW tilde T, so that appears here, plus dZT dWt, so the multiplication of this term and this term. Now here we see this one appearing with a plus sign, with a minus sign, so here we see this one appearing with a minus sign, minus CT theta T dWt dWt. And here we see that, and dWt dWt is dt, of course, with a minus sign, and here we see it with a plus sign. So these two will cancel out, and the rest will remain. So we will see at least 3 terms appearing. So we have minus ZT theta T W tilde T dWt, the first term here, plus ZT dWt, that is that term over here. And then we have some terms canceling out. That is this one plus ZT theta T dt. That will cancel out with this one minus ZT theta T dt. And the last term here, that is a dWt dt term, that is a cross variation, which is also equal to 0. So that also cancels out. So what remains is that this is, in fact, if we take ZT out, this is 1 from here minus theta T W tilde T times ZT dWt. And if we look at this, we see that W tilde T ZT is in fact an Ito integral with respect to WT. So here we see WT. It is an Ito integral with respect to WT, and hence it is a martingale under P. So that concludes the first claim. And the second claim, that W tilde T is a martingale under P tilde, we do it as follows. It is in fact a consequence of the theorem 5.2.2 that we have just seen. And that is as follows. First of all, it's clear that W tilde T is Ft measurable. That's a first. Then, now let S be less than T. And because W tilde T is Ft measurable, we have the following. The expectation under P tilde of W tilde T given Fs, so the conditional expectation of W tilde T given Fs, the information up to time S, that is by 5.2.2, that is 1 over Zs, the expected value of W tilde T ZT Fs. Now W tilde T ZT is in fact, we have just shown that this is a martingale under P. So given Fs, this is equal to W tilde S ZS, right? It is a martingale under P. So this is W tilde S ZS. And if we multiply by 1 over ZS, then these two cancel out. And in fact, what we get is W tilde S, what we want, right? So in fact, if we look at that, that tells us that W tilde T is a martingale under P tilde. And then by Levy's characterization, it is a Brownian motion. And this concludes the lecture for today. I thank you for your attention.